Okay, it is recording. Right. So what I was talking is that we will be studying today about two things. One is process corner analysis, and second is Monte Carlo. Right. What are the two different things? Process corner analysis and Monte Carlo analysis. Let me tell you two things that usually students take these variations as a similar variations as far as the study of these variations are concerned, but actually these are two different variations, right? So we most of us know that how to do these variations, but it is very important to learn that what is the theory behind these process corner simulations. I'm sure most of you know about what is a Monte Carlo simulation or process corner simulation. If you don't know, we can do the experiment first, then I can let you know. If you all know how to what about these uh, what these terms are, then I can explain the theory part, because theory part is more important in this case. Practical, most of us know how to do that. Just give me a second. I mean, there is some problem with screen sharing. Okay. So as I told you that there are two different things. One is process corner analysis, one is Monte Carlo analysis, and we would be doing both. Uh, Process corner analysis means that you will be using NMOS and PMOS in two different ways. What are these ways? These ways include that I can have four things. One is TT, rather five things: SS, SF, FS, and FF. This means that in my analysis, I can see in when I see TT, when I say SS, this first is for NMOS and second is for PMOS. Means when I talk about my journal simulations, then I take TT means typical NMOS and typical PMOS. Similarly, when I talk about SS, it's slow NMOS and slow PMOS. When I talk about SF, means I'm saying slow NMOS and fast PMOS. When I say FS, means fast NMOS and slow PMOS. Similarly, the term remain is FF, that says fast NMOS and fast PMOS. Now, what is the difference between this slow and fast term? Actually, whenever you write any academic paper or you do some sort of a research, usually the researchers ask you or the reviewers ask you to do the PVT simulation. Either you work on the analog VLSI circuit design or you work in the digital VLSI circuit design. In both cases, if you do not do PVT simulations, the results are not taken as the valid results or the good results. So what is the meaning of PVT? PVT is P stands for process corner, V stands for voltage, and T stands for temperature. Means you need to test your circuit on different voltages, on different temperatures, So these are the parts of your, these are the essential part of your any academic research or any academic analysis. Whenever you create a circuit, I'm repeating, whether you work on the analog design or you work on the digital design, you have created a circuit, you have got some power results, or you have some got some delay results. I repeat this thing that these results are not enough. Once you have got a few results, for example, I'm working on the 45 nanometer. So if I have got results on 1 volt of 45 nanometer that are not enough, industry will not accept it. Your results are supposed to be found on from 0.5 volt to 1 volt on every voltage. This analysis is to be done because 0.5 volt is the minimum voltage on which you are working, and 1 volt is the maximum voltage which is defined in your this PDK, process design kit. So in that case, from 0.5 volt to 1 volt, you have to work on every voltage. When I show you the results in this class, I show you result on zero point 0.8 volt, I show the 0.7 volt, but that doesn't mean these are the complete results. You need to find the results from 0.5 volt to 1 volt on every voltage. Why it is said so? Because if you see that when you use 0.5 volt, you will get the, you are using the minimum voltage. Minimum voltage means from this voltage you will get the minimum current of your circuit. Minimum current of your circuit means you will get the maximum delay and minimum power consumption of your circuit. Uh, Anyone of you who is having any doubt on what I'm saying, if you are using the minimum voltage, let us say 0.5 volts, in this case, you are using the minimum voltage. For minimum voltage, you will get the minimum current. For minimum current, you will get the minimum, maximum delay and minimum power consumption, be it static or dynamic. The power dissipation will be minimum in any case, right? So what we have seen in this case is that when you use these terms, whenever you use these things, like PVT sort of a thing, whenever you read in any analysis or somebody tells you to do the PVT analysis, it means you have to do the analysis from 0.5 volt to 1 volt on every voltage, right? This is the voltage analysis. What about the current analysis? In the current analysis, when somebody tells you to do the analysis on current, then it when somebody tells you to do analysis on temperature, it means that you have to work on the different temperatures. Means you can work from minus 60 degrees Celsius to 160 degrees Celsius. These are the arbitrary values I'm telling you. I repeat, I'm telling you the arbitrary values. This actually depends on the environment in which you are going to implement your IC. For example, if you are going to implement your IC in the this flat Earth region, then in that case, what is the minimum temperature this Earth sees? Suppose you are going to implement in India, so minimum temperature you will see in Siachen, then you will be working on somewhere minus 20 degrees Celsius, minus 30 degrees Celsius. So you start testing from minus 50 degrees Celsius. And what is the maximum temperature that you see? You see in Rajasthan 52, 53 degrees centigrade. So you see your IC to work up around 70 degrees centigrade. You test on these voltages depending on the application of your IC. On different temperatures depending on the application of your IC. And this is called temperature variation analysis. For example, if somebody is implementing a memory which is to be placed in the space, now space can have the higher temperature. There can be a temperature like higher in the range 200 degrees Celsius, 300 degrees Celsius. If you are to implement it over there, then in that case you have to test your IC accordingly. The investigator may ask you to implement the actual temperatures which the IC is going to see in the higher space. Now, what is the, we have seen what is the voltage variation. Voltage variation we have seen from minimum voltage implemented to maximum voltage. So we have seen that temperature variation, VT variation. This variation is this PT, SS, SF, FF. These are called process corner variations. I will show you in your this theory and this practical analysis that how you do this process corner variation analysis. Right. Then we will first do the process corner variation analysis on one circuit. Then we will go for the theory of the Monte Carlo simulation. Why do we do Monte Carlo simulation? And then we'll do the Monte Carlo simulation also. So let me show you how do we do process corner variations. So I'll open the terminal. Okay. So I'll open, let us say, some inverter. Or you can use it on any circuit of your choice. I'll use the ADL. So this is your ADL where I have given the pulse on the input and ground and VDD as a voltage X, and this X voltage is actually 0.8 volts, right? So I need to see the power results also in this case. So I'll get to save all. And then I do the simulation. Once I've done the simulation, I'll go for the formula for power. Go to result browser, transient, calculator. I hope you all have done the practice and you know this process. That is why I'm doing it on a brisk pace. The average value, and that's how we put it on ADL. And I'll write it here. Power. Okay. Now I'll see the delay. For delay, I have the simulation already done. So I'll go for the term delay. For delay, I'll first go for the input. Similarly, I'll go for the output. Then I'll apply and then I'll put it to ADL. Right? Delay. Okay. I'll very soon I'll show you that why do I require both of these things. Now, whenever I do the simulation, or before doing simulation, please see that I have used this is the model library, and this is your setup. There, when you double click, you see all these process corners. Typical, fast, slow, fast, slow, fast, Monte Carlo. So I'll take both typical values, apply, and then I'll do the simulation. Let us note down the value. The power dissipation is 9.225 nanowatts and delay is 33.589 picoseconds. Now, what I'm going to do is I'm going to implement PMOS and NMOS both fast. What is the meaning of fast PMOS and NMOS? Fast means the threshold voltage is low in this case. When threshold voltage is low, there will be higher current. See, process corner means in extreme conditions, how fast your NMOS can be and how fast your PMOS can be. It is about the saturation current of the highest value. Somehow, if your NMOS uh, get some corruption due to this external noise environment or any other environmental condition, what will happen to your simulation? What will happen to your results? So when you have, suppose this environment has impacted both PMOS and NMOS. In that case, we are assuming that both NMOS and PMOS both have gone faster due to this impact. In this case, if I do simulation, then this will be the change in the power and delay. See, my power has gone to 8.84 nanowatt and the delay has gone to 25.52. Both devices are fast now, so the result has gone faster. You see, the power consumption was 9.22 nanowatt. It has come down to 8.84 nanowatt. And the delay was 33.589. Now it has become 25.52. The delay has reduced. Means your device has gone faster. It is consuming less power, but I'm repeating, you cannot do this on your IC from yourself. These are the environment based conditions or by the life or by the time. If this kind of a condition comes in, then what will be the extreme results? That is, we see in the process current analysis. It is the extreme results if my NMOS and PMOS both get faster. Now I'll see some other results. See, remember the delay was 25.52 when both get faster. Now let us assume that both have gone slower. This is slow mode. Now what you see in slow mode, the power dissipation is 9.70 and the delay is, see, the delay is 42.01. The the normal delay was 33 picoseconds. Now because both devices have gone slow, so the delay has gone to 42 picoseconds. There is 9 picosecond rise in the delay, right? Similarly, if you go for the corner, any other corner we can choose. Let us go for slow, fast, slow NMOS, fast PMOS. What will happen in this case? Slow NMOS, fast PMOS is usually taken as the worst case corner in many cases. It is taken as worst case corner in many cases. See, the power dissipation is 9.27 and the delay is 38.2656. Now, you please see that these are actually the impact of the process corners. Any of you have, if you have any question on this process corner analysis, I've shown you almost all the corners. One corner is left, which is called FS. That I also show you the results. It again impacts and it shows. This shows that 9.17 nanowatt is the power and 28.97 is the delay. So every process corner impact your device in every possible way, in different possible ways. We have seen these are only four cases possible. If your NMOS goes fast and PMOS goes slow. If your NMOS goes slow, PMOS goes fast. Both get fast, both get slow. These are the only four possibilities for assumptions. Now the other analysis was that if you want, this is called the temperature. Now you see what is the result. You see the result on a particular process corner. The process corner is this process corner is FS process corner. Let me see if suppose there is a SS process corner. Both are slow. Then what are the results? The results are 9.70 is a power consumption and 42 picosecond is a delay. Now, the temperature is 27 degrees Celsius. Now, if I assume that the temperature is 0 degrees Celsius, right? If I assume that on this process corner, slow process corner, the temperature is 0. Now, what will happen to the results? You see, the power dissipation is now 9.58 and the delay is 42.25, right? The power dissipation has come down. It was 9.70 in case when on the room temperature 27 degrees Celsius STP, and it is 42.25. It was 42.01. Means as you decline the temperature, the power dissipation comes down and the delay goes higher. Now let us see the high temperature. Suppose let us say 100 degrees Celsius. On 100 degrees Celsius, if I see this, my power dissipation increases and the delay almost remains the same. So these are the impact of temperature on your device. You can check the impact of temperature. Normally we keep it on default value, 27 degrees centigrade. You can check your device from 0 degrees centigrade to 100 degrees centigrade or whatever temperature, in whatever temperature your device is going to be implemented, right? So now let me change the process corner to typical again. So these are the process corner simulation. These are the temperature variation. This is the process corner variation. And I can change the voltage also. If I change the voltage from here, I'll start getting the other results. Please ask if you have any question till here. Then I'll move to the other part, which is called the Monte Carlo. Any doubts till here? We are done with the process corner analysis, where we have assumed that my NMOS, if what will happen if my NMOS goes slow? What will happen if my PMOS goes slow? What will happen if my PMOS goes slow and NMOS goes high? Because of any conditions, because of heat, environmental conditions, their mobility, concentrations. So if this happens to your IC, what will be the extreme results? Because sometimes you see on the manual of your device, whenever you get a device, suppose you get your phone or you get your computer, you see the manuals. You see what is the maximum possible current, what is the minimum possible current. This is because of they test the device on all the possible process corners and temperatures. They tell you that do not operate this device below this temperature, do not operate this device above this temperature, because of this temperature analysis only. They know that if you will use your device above or below that specified temperature, you may get some arbitrary results. So that is why these specifications and simulations are necessary, right? Please tell me if you have any query, then I'll come to the Monte Carlo analysis.
Excuse me, sir.
Yes, please ask.
सर मतलब कि ये जो प्रोसेसिंग पैरामीटर्स हैं, इसे स्लो फास्ट मतलब ये कन्वीनियंट है कि मतलब आपको अगर कोई भी चेक करने के आपका स्लो चल रहा हो फास्ट चल रहा हो तो आपको हमेशा W और L चेंज नहीं करना पड़ेगा।
नहीं
तो
आपने शिवांश, ऐसे होता है कि आपने एक बार एक डिवाइस बना लिया, उस डिवाइस को बनाने के बाद आपने इसे ऑप्टिमाइज भी कर लिया। अब जब आप उस डिवाइस को अपने रिजल्ट्स दे रहे हो फाइनली कि ऑप्टिमाइज करने के बाद मेरी ये रिजल्ट्स हैं, तब ये रिकमेंडेशन होती है कि आप इनको प्रोसेस कॉर्नर में भी चेक करो, क्या आपके ऑप्टिमाइज रिजल्ट्स, इफ दे रिमेन ऑप्टिमाइज्ड ऑन दीज पैरामीटर्स आल्सो, अगर वो देखो एनवायरमेंट के हिसाब से आपका पीमोस और एनमोस अपने आप को शिफ्ट करेगा, उसके अंदर जो मोबिलिटी है, जो इलेक्ट्रॉन्स हैं, अगर वो सपोज स्लो हो जाए किसी वजह से, टेम्परेचर की वजह से हो जाए, किसी वजह से हो जाए, या पीमोस फास्ट हो जाए, तो उस केस में आपका डिवाइस कैसे बिहेव करेगा, आपके रिजल्ट्स कितना ऊपर और कितना नीचे जा सकते हैं, राइट? दिस शोज द प्रोसेस फॉर एनालिसिस. प्लीज गो ऑन इफ यू हैव एनी काउंटर क्वेश्चन.
नो, थैंक यू सर।
ठीक है, आप देखो, what is the use of using this process for analysis is that you get minimum and maximum value of your parameters of your particular device. If you are going to work on the power and delay only, you will get the value of power and delay. Suppose you are working on analog, you find some value of transconductance or you other values. In that case, all these values you can find, or all these values you can use as a specification of your device, because you have done the process corner simulation. It is very important whenever you will do any academic research or whenever you create any circuit, any expert may ask you that whether you have tested your device on different process conditions, or whether you have tested your device for different temperatures, or whether you have tested your device for different voltages. These are the basic important things. Now I'll come to the Monte Carlo simulation. If nobody has any other question, if you have any question, you can stop me anywhere. You can ask me questions, because this is a very important part. Even if you know everything about your device, even if you know everything about your circuit, and you have not done these process corner or Monte Carlo simulations, your results remain incomplete always. Now, what is the Monte Carlo simulation? These are the higher side of your process curve analysis. What is a Monte Carlo simulation? See, Monte Carlo simulation is like running thousands of circuit simulations together. I'm repeating my words: running thousands of circuit simulations together with random variations. Like, कौन सा random variation? The random variation of VTH, the random variation of width, random variation of length, random variation of oxide thickness, random variation of doping, etc. Now you will say that, sir, we can change only one parameter in this. Then why we are how can we do all these random variations? These values are generated automatically in your simulator. Everybody knows that these values depend on the manufacturing conditions. But just assume you have created two different transistors on a wafer. Now these two different transistors will never be the same. Why these will never be the same? Because the doping concentration inside both transistor may or may not be same. The oxide thickness of your SiO2 may or may not be same. There can be some 2, 3, 4, 5% change. Uh, because this oxide thickness is not same, that is why your threshold voltage may or may not be the same. Your device may or may not have exact 45 nanometer. It can be 44.9 nanometer. It can be 45.1 nanometer. It can be 45.95 nanometer. 44.95 nanometer. So these kind of variations are possible. You say that I'm using 300 nanometer width. If it is possible that during manufacturing it becomes 299 nanometer width, then what will you do? Similarly, when you do dope your PMOS, the default doping concentration is giving some value in your simulator, and you actually end up with having 5%, 7% lesser doping, because in manufacturing you cannot create 100% ideal device. So that is why it is very important that you simulate your device with all these different conditions. You change all these values and why do thousands of simulations? Because you do variations in this, keep these same. Then you do variation in this, you keep these three same. Then you do variation in both of these, keep them same. So you make thousands of such combinations and start doing simulations. Then you get certain values. Out of those values, you will get some minimum value, you will get some maximum value. That becomes your your simulation extremes in Monte Carlo simulation. That is why Monte Carlo simulation is very important. See what what these simulations will give you. These will give you uh, uh, a lot of statistical insights. Like this will give you parameter sensitivity. How sensitive is your parameter? Suppose you said you have claimed that my device is going to have 32 picosecond delay, and your Monte Carlo simulation is saying the minimum is 28 picosecond and the maximum is 42 picosecond. Then you cannot claim 32 picosecond. You will say that my device may have 28 picosecond, may have 42 picosecond, but there is a maximum possibility of 31 picoseconds. That will show when you will give statistical plot and you get plot like this, and there you get certain value here at 31 picosecond. Then you say that I can have 28 picosecond, I can have 42 picosecond, but there's a maximum possibility of getting 31 picoseconds. That is why Monte Carlo simulation is important. And Monte Carlo simulation, remember, it is computationally intensive. It is used in Cadence Virtuoso for, you will read two words with Cadence Virtuoso. It gives you either a global mismatch or local mismatch. Now, what are these two terms? These are very less used in this digital VLSI, but these terms are mostly used in analog VLSI design. But you should know what is the difference. Uh, See, the global simulation, this global mismatch. What is a mismatch? First, you should understand what is the meaning of this term mismatch. The term mismatch means that whatever values of this VTH, WL, TOX you have assumed, the values, the actual practical values are not matching with these values. This is called mismatch. Now, what is a global mismatch and what is a local mismatch? The global mismatch means the same variation has been applied to every transistor. For example, I'm applying the slow corner. So the same variation has been applied to every transistor in inter-die wafer to wafer effect, but it has been done statistically. For example, if I have done the corner analysis or if I have done any global mismatch study, then I have considered the whole wafer. On every transistor VTH changes, on every transistor WL changes, on every transistor TOX changes. This is called global mismatch. Now, what is a local mismatch? Local mismatch means that you have created a circuit. Here you have 5% variation. Here you have 7% variation. Here you have 3% variation. For every transistor and to their neighbor, there are different variations. So this is called local mismatch. In Monte Carlo analysis, when we do it on Cadence Virtuoso, we see both local and global mismatches. We assume local and global mismatches. And these mismatches are not only +3, +5%. This can be ±3%. This can be ±5%. This depends on how much randomness you have chosen for your device. I hope I have made my point clear that what is the difference between process corner and what is the difference between Monte Carlo. In process corner, you have only 5 different corners: typical, slow, fast, slow, or fast. And then there is a temperature analysis, and then there is a voltage analysis. In Monte Carlo simulation, you have process corner analysis, temperature analysis, voltage analysis, VTH analysis, this width and length variation, oxide thickness variation, doping concentration variation, all sort of variations you do. That is why people, when you will see the research papers, people do 5,000 point simulation, 10,000 point simulation. The more points you take, the more accurate will be your results. And that's how you do the Monte Carlo simulation. Now we are closing this meeting for in this minute, and then we'll join again on the same link, and we'll do the Monte Carlo simulation practically on the same circuit, and we'll see the results. So let's join on the same link again. This link is going to close at any second. You can leave